The gradual, often imperceptible erosion of skeletal muscle mass and strength, clinically recognized as sarcopenia, represents one of the most profound and insidious threats to the independence, vitality, and overall health span of the aging population. For decades, the medical community and the general public alike have largely accepted this physiological decline as an inevitable consequence of advancing chronological age, a one-way trajectory toward frailty, decreased mobility, and ultimately a loss of physical autonomy. However, contemporary advancements in biomechanics, cellular biology, and nutritional science have unequivocally shattered this fatalistic paradigm, revealing that the aging human body retains an astonishing, highly responsive capacity for continuous muscular regeneration and functional restoration. Overcoming this progressive skeletal muscle atrophy requires a radical departure from conventional, low-intensity exercise recommendations, necessitating instead a highly targeted, scientifically rigorous blueprint that prioritizes the precise application of mechanical tension, specific nutritional signaling, and profound neuromuscular engagement. By meticulously engineering interventions that focus on eccentric loading protocols, the deliberate recruitment of high-threshold motor units, and the precise integration of leucine-rich protein synthesis, it is entirely possible to bypass the systemic hurdles of age-related anabolic resistance. Furthermore, when these biomechanical and nutritional strategies are coupled with the psychological practice of visualizing cellular repair, older adults can actively orchestrate the resurrection of dormant type 2 muscle fibers, thereby forging a definitive path toward restoring independent mobility and comprehensively reversing the debilitating cycle of age-related frailty. To truly understand how to reverse muscle atrophy, one must first explore the complex microscopic environment of skeletal muscle tissue and the specific mechanisms through which it degrades over time. Skeletal muscle is not merely a mechanical tissue that pulls on bones to create movement. It is a highly dynamic, metabolically active endocrine organ that communicates continuously with the brain, the immune system, and the metabolic regulatory centers of the body. Within the architecture of a muscle belly, there are thousands of individual muscle fibers, primarily categorized into two distinct types: Type 1 slow-twitch fibers and Type 2 fast-twitch fibers. Type 1 fibers are highly oxidative, dense with mitochondria, and designed for sustained, low-intensity endurance activities, such as walking or maintaining posture. In contrast, Type 2 fibers are larger, produce significantly more force, contract much more rapidly, and are heavily reliant on glycolytic energy systems. These fast-twitch fibers are the biological engines responsible for explosive movements, heavy lifting, and the rapid, corrective balance adjustments required to prevent a catastrophic fall. The tragedy of age-related sarcopenia is that it does not affect all muscle fibers equally. It is characterized by a disproportionate, targeted denervation and profound atrophy of the Type 2 fast-twitch fibers. As individuals age, a combination of decreased rigorous physical activity, hormonal shifts, and neurological decline leads to the progressive disconnection of the motor neurons that innervate these powerful Type 2 fibers. Once a muscle fiber loses its neural connection, it enters a state of apoptosis, or programmed cell death, and the functional contractile tissue is gradually replaced by non-contractile intramuscular fat and fibrotic connective tissue, a process known as myosteatosis. This specific loss of Type 2 fibers explains why many older adults may still be able to walk long distances slowly, but struggle immensely to stand up from a deep chair, climb a steep flight of stairs, or catch themselves when they stumble. Therefore, any effective strategy designed to reverse frailty and restore functional independence must specifically and aggressively target the reactivation, hypertrophy, and neural re-education of these critical type 2 fast-twitch muscle fibers. The primary biomechanical mechanism for awakening and stimulating these dormant type 2 fibers lies in the strategic application of mechanical tension, specifically through the prioritization of eccentric loading. In the realm of muscle physiology, a muscle contraction can be categorized into 3 phases: concentric, isometric, and eccentric. The concentric phase occurs when the muscle shortens under tension, such as when lifting a weight against gravity. The isometric phase involves the muscle generating force without changing its length, much like pushing against an immovable wall. The eccentric phase, however, occurs when the muscle lengthens while actively producing force, effectively acting as a braking mechanism to decelerate a load against gravity, such as slowly lowering a heavy object to the ground or controlling the descent when sitting down into a chair. Traditional exercise programs prescribed to the elderly heavily emphasize the concentric phase, often utilizing light weights lifted repeatedly, which overwhelmingly stimulates the already preserved type 1 endurance fibers while leaving the crucial type 2 fibers largely unchallenged and unstimulated. Eccentric loading fundamentally alters this physiological equation. Because of the unique sliding filament mechanics within the muscle sarcomeres, where the myosin heads grip the actin filaments and are forcibly pulled apart during lengthening, eccentric contractions can generate up to 40% more force than concentric contractions while simultaneously requiring significantly less metabolic energy and oxygen consumption. This unique phenomenon makes eccentric training an exceptionally powerful, highly efficient tool for older adults, particularly those who may suffer from cardiovascular limitations or reduced respiratory capacity. When an aging muscle is subjected to controlled, heavy eccentric loads, the extreme mechanical tension causes micro-tears in the ultrastructure of the muscle fibers, specifically targeting the Z-lines of the sarcomeres. This controlled microtrauma is not an injury, but rather a profoundly necessary biological stimulus. It triggers a massive cascade of mechanotransduction, a process where the physical force of the stretch is converted into chemical signals within the cell. These signals forcefully awaken satellite cells, which are specialized muscle stem cells lying dormant on the periphery of the muscle fibers. Upon activation by eccentric stress, these satellite cells proliferate, differentiate, and donate their nuclei to the damaged muscle fibers, profoundly expanding the myonuclear domain and providing the essential genetic machinery required to synthesize new functional contractile proteins, thereby directly rebuilding the lost architecture of the type 2 fibers. Furthermore, the implementation of eccentric loading strategies serves as a profound neurological intervention, specifically addressing the critical need to recruit high-threshold motor units. A motor unit consists of a single motor neuron originating in the spinal cord and all the individual muscle fibers it innervates. According to Henneman's size principle, a foundational law of neurophysiology, the central nervous system recruits motor units in a strictly sequential order based on the demand for force. Low-demand activities, such as light walking or lifting a very light weight, only recruit small, low-threshold motor units associated with type 1 slow-twitch fibers. The large, powerful, high-threshold motor units that control the type 2 fast-twitch fibers remain entirely dormant until the demand for force exceeds the capacity of the smaller units. Because many older adults unconsciously modify their daily behaviors to avoid heavy lifting or explosive movements, these high-threshold motor units can go entirely unused for years, leading to an insidious neurological decoupling. Eccentric loading, by virtue of the massive mechanical forces it generates, effectively bypasses this neurological inhibition. When an elderly individual is guided to slowly lower a resistance that is heavier than what they could comfortably lift concentrically, the nervous system is forced into a state of high alert, dramatically increasing the rate coding. The frequency of neural impulses sent from the brain to the muscle, and aggressively recruiting those dormant high-threshold motor units to prevent the load from collapsing. This intense neuromuscular demand fundamentally rewires the communication pathways between the central nervous system and the peripheral skeletal muscles. It enhances the myelination of the motor neurons, improves the release of the neurotransmitter acetylcholine at the neuromuscular junction, and synchronizes the firing of multiple motor units simultaneously. This neural rejuvenation is the secret catalyst behind the rapid strength gains often observed in the initial weeks of a properly structured resistance training program for the elderly. Before significant structural muscle hypertrophy even occurs, the individual becomes profoundly stronger and more physically capable simply because their brain has relearned how to access and command the muscular horsepower they already possess. This restoration of neural drive is absolutely essential for the rapid, forceful muscle contractions required to maintain balance, adjust posture in real time, and ultimately prevent the devastating falls that so often precipitate the loss of independence in the aging population. However, the powerful mechanical stimulus provided by eccentric loading and the enhanced neural drive of high-threshold motor unit recruitment represent only one half of the physiological equation required to reverse muscle atrophy. The other half relies entirely on highly specific, targeted nutritional interventions designed to overcome a formidable biological barrier known as age-related anabolic resistance. In a healthy young adult, the ingestion of dietary protein or the performance of resistance exercise triggers a robust spike in muscle protein synthesis, the biological process by which the body builds new muscle tissue. As the human body ages, the skeletal muscles become progressively deafened to these anabolic signals, a phenomenon driven by chronic low-grade systemic inflammation, often termed inflammaging, alongside decreased blood flow, hormonal downregulation, and cellular insulin resistance. Because of this anabolic resistance, an older adult requires a significantly higher dose of protein to trigger the same muscle-building response that a much smaller dose would elicit in a younger person. The traditional dietary recommendation of consuming a modest amount of protein spread evenly throughout the day is categorically insufficient to breach this elevated anabolic threshold in the elderly. To force the aging muscle to synthesize new tissue, we must aggressively manipulate the intracellular signaling pathways, specifically targeting the mechanistic target of rapamycin complex 1, universally known as mTORC1. mTORC1 acts as the master biological command center for muscle growth. It is an intracellular sensor that constantly evaluates the mechanical stress placed on the muscle, the availability of cellular energy, and, most importantly, the concentration of specific circulating amino acids. When mTORC1 is fully activated, it initiates a complex cascade of genetic transcription and translation, prompting the ribosomes within the muscle cells to begin rapidly assembling new contractile proteins, thereby repairing the microtrauma induced by eccentric exercise and resulting in tangible muscle hypertrophy. The most critical nutritional key to unlocking this mTORC1 pathway and overriding anabolic resistance is the essential branch chain amino acid leucine. Leucine is not merely a passive structural building block for new muscle tissue. It is a highly active, potent signaling molecule that directly binds to and activates the proteins upstream of mTORC1. In the context of age-related muscle atrophy, the concentration of leucine in the bloodstream must reach a specific elevated threshold, often referred to as hyperaminoacidemia, to effectively turn on the muscle-building machinery. Scientific evidence demonstrates that older adults require an acute dose of approximately 3 to 4 grams of pure leucine per meal to maximize muscle protein synthesis, a dramatic increase compared to the needs of younger individuals. This specific leucine threshold cannot be easily achieved through casual dietary habits. It requires the deliberate, strategic consumption of high-quality, rapidly digestible protein sources. Animal-derived proteins, particularly whey protein isolate, are exceptionally rich in leucine and are absorbed into the bloodstream with remarkable speed, creating the rapid spike in circulating amino acids necessary to forcefully trigger the mTORC1 pathway. By meticulously timing the ingestion of these leucine-rich protein sources to coincide with the post-exercise recovery window, the period when the muscle cells are most exquisitely sensitized to nutritional inputs due to the prior mechanical tension of eccentric loading, we create a profoundly powerful, synergistic anabolic environment. The mechanical stretch of the exercise opens the cellular pathways, increasing the permeability of the muscle fiber membranes, while the surge of leucine forcefully commands the nucleus to begin the intricate process of building new actin and myosin filaments. This precise, orchestrated integration of intense mechanical tension and high-dose leucine signaling completely circumvents the blunted anabolic response of the aging body, effectively forcing the skeletal muscle to regenerate, rebuild its lost mass, and restore its functional structural integrity. Transitioning from the biomechanical and nutritional realms, we must comprehensively address the vital, yet profoundly underutilized psychological and neurological dimensions of reversing age-related muscle atrophy, particularly the immense power of the mind-muscle connection and the practice of visualizing cellular repair. The human brain is not a static organ. It possesses a remarkable, lifelong capacity for neuroplasticity, the ability to continuously form and reorganize synaptic connections in response to learning, experience, and focused attention. In the context of restoring mobility and combating frailty, this neuroplasticity can be explicitly harnessed to amplify the physiological effects of physical training. When an older adult engages in eccentric resistance exercises, the simple act of moving the weight from point A to point B is insufficient to maximize the regenerative potential. They must be guided to cultivate an intense, deliberate internal focus, actively visualizing the specific muscle fibers lengthening under tension, absorbing the mechanical load, and firing with electrical precision. This intense psychological concentration on the working muscle dramatically alters the neurological output from the motor cortex of the brain. Studies utilizing electromyography and functional magnetic resonance imaging have definitively proven that when an individual actively thinks about the muscle they are contracting, the electrical amplitude of the signals sent down the spinal cord increases significantly, leading to a much higher percentage of motor unit recruitment. For the aging individual struggling to awaken dormant type 2 fibers, this focused mental engagement acts as a neurological amplifier, ensuring that every repetition performed maximizes the neural drive and forces the stubborn, high-threshold motor units into action. Beyond the immediate neuromuscular enhancement during exercise, the broader psychological practice of visualizing cellular repair plays a crucial role in mitigating the systemic physiological stress that often accompanies aging and physical decline. The mind and the endocrine system are inextricably linked. Chronic psychological stress, anxiety, and the pervasive fear of losing independence, a state heavily prevalent among the frail elderly, trigger the persistent release of cortisol, a highly catabolic stress hormone that actively breaks down muscle tissue, suppresses the immune system, and directly antagonizes the anabolic effects of testosterone, insulin-like growth factor 1, and mTORC1 activation. By guiding older adults to engage in daily periods of deep, focused visualization, where they mentally picture the leucine molecules entering their muscle cells, the satellite cells proliferating to repair the micro-tears, and their muscle fibers growing thicker and stronger, we can induce a profound state of parasympathetic nervous system dominance. This deliberate mental practice effectively lowers systemic cortisol levels, reduces the circulation of inflammatory cytokines, and optimizes the internal biochemical environment for muscle protein synthesis. Furthermore, this visualization process directly combats a deeply ingrained psychological barrier known as kinesiophobia, the debilitating fear of movement and physical exertion that often develops after a fall or a period of prolonged illness. As older adults vividly imagine themselves moving with strength, stability, and control, they actively rewrite the neurological scripts of learned helplessness that dictate their physical limitations. They begin to rebuild profound self-efficacy and neuromuscular confidence, effectively convincing their central nervous system that their body is capable, resilient, and safe to engage in the rigorous physical efforts required to stimulate true biomechanical adaptation. The ultimate objective of this exhaustive, integrated approach, combining eccentric biomechanical loading, high-threshold motor unit recruitment, leucine-rich nutritional signaling, and profound psychological visualization, is not merely the aesthetic accumulation of muscle tissue, but the profound, life-altering translation of newly forged muscle mass into dynamic functional independence. Skeletal muscle is the primary shock absorber of the human body, the biological armor that protects the skeletal structure, stabilizes the joints, and orchestrates complex, multiplanar movements. As the targeted type 2 fast-twitch fibers regenerate and hypertrophy, the immediate, tangible result is a dramatic increase in the individual's rate of force development, which is the speed at which a muscle can generate its maximum strength. This specific physiological metric is the single most critical determinant of an older adult's ability to safely navigate their environment. When an elderly person trips on an uneven sidewalk or loses their balance on a staircase, absolute baseline strength is not what saves them. It is their rate of force development, their ability to recruit those powerful type 2 fibers in a fraction of a second to explosively thrust a leg forward, stabilize their center of gravity, and arrest the fall before it occurs. As their eccentric strength improves, their ability to decelerate their own body weight is restored, allowing them to confidently lower themselves into a chair without collapsing, descend a flight of stairs with smooth, controlled precision, and navigate complex terrain without the constant, terrifying fear of a catastrophic injury. Moreover, the process of regenerating muscle tissue through heavy, controlled eccentric loading profoundly enhances the body's proprioceptive capabilities. Proprioception is the central nervous system's continuous, subconscious awareness of the body's position and movement in three-dimensional space, governed by specialized sensory receptors called muscle spindles and Golgi tendon organs located deeply within the muscle fibers and tendons. Age-related muscle atrophy and prolonged physical inactivity severely degrade this sensory feedback loop, leaving the elderly feeling disconnected from their limbs, unsteady on their feet, and heavily reliant on visual cues to maintain their balance. The intense mechanical tension and structural microtrauma induced by eccentric exercise forcefully stimulate these proprioceptive receptors, effectively rebooting the sensory communication lines between the peripheral limbs and the brain. as the structural integrity of the muscle is rebuilt through the synergy of leucine-driven protein synthesis and mechanical mechanotransduction. The muscle spindles become acutely sensitive to changes in length and tension once again. This enhanced proprioception translates directly into a smoother, more confident, and significantly faster gait speed. The individual no longer shuffles hesitantly, dragging their feet to maintain contact with the ground. Instead, they walk with purpose, fully capable of lifting their legs, extending their hips, and dynamically interacting with their physical environment. In the broader context of systemic health, the regeneration of skeletal muscle mass acts as a powerful, cascading catalyst that positively influences nearly every other physiological system in the aging body. The newly built, metabolically active type 2 muscle fibers act as a massive glucose sink, dramatically improving the body's sensitivity to insulin and effectively combating the onset of age-related type 2 diabetes. As the muscle contracts and lengthens against resistance, it acts as an endocrine organ, releasing highly beneficial anti-inflammatory proteins known as myokines, specifically interleukin-6, directly into the bloodstream. These myokines actively counteract the systemic, low-grade inflammation of inflammaging, reducing the oxidative stress on the cardiovascular system, improving endothelial function in the blood vessels, and promoting healthy cognitive function by stimulating the release of brain-derived neurotrophic factor, a vital protein that supports the survival and growth of neurons in the brain. The physical act of stressing the muscle, pulling forcefully against the tendons, also provides the necessary piezoelectrostimulation to the underlying bones, driving the accumulation of new bone mineral density and directly combating the parallel epidemic of osteoporosis. Therefore, by intensely focusing on the regeneration of skeletal muscle, we're not treating a single symptom of aging. We are fundamentally engineering a holistic, systemic revitalization of the human organism. Ultimately, the blueprint for overcoming age-related muscle atrophy and reversing the trajectory of frailty requires a profound paradigm shift in how we view the capabilities of the aging body. We must discard the outdated, overly cautious methodologies that treat the elderly as fragile entities requiring only gentle, passive movement. Instead, we must embrace the rigorous, undeniable science of human physiology, recognizing that skeletal muscle, regardless of chronological age, remains a highly adaptive, remarkably resilient tissue that yearns for a precise, potent stimulus to survive and thrive. By systematically prioritizing eccentric mechanical loading to induce necessary microtrauma, deliberately recruiting dormant high-threshold motor units to restore the central nervous system's neural drive, precisely manipulating the mTORC1 pathway through targeted, high-dose leucine-rich protein synthesis to shatter the barriers of anabolic resistance, and empowering the individual to actively visualize and psychologically orchestrate their own cellular repair, we provide a master key to unlock the body's dormant regenerative potential. This comprehensive, multifaceted biomechanical and biological strategy does not simply delay the inevitable decline. It actively reverses the biological clock of the muscular system, restoring the powerful, explosive type 2 fibers that are the very foundation of physical autonomy. It ensures that the later decades of life are not defined by a shrinking perimeter of existence, physical dependence, or a fearful, steady decline into immobility, but rather by profound physical resilience, unassisted vitality, profound neuromuscular confidence, and the enduring, joyful freedom of absolute, uncompromised independent mobility.